All right, welcome back, everybody. In this video, we're looking at what exactly it means to solve a differential equation. Last video, we saw where differential equations could come from, that they are, in some sense, describing physical laws, and that we would like to figure out which functions actually obey those physical laws. And in order to start the video, I have to define for you what we mean by a solution to a differential equation. Now, on the board here, remember if we have some sort of algebraic equation, right? If I have something that looks like this, then we understand that this x here is an unknown that we are trying to solve for. That there is potentially some number that satisfies this equation. And if I walk through some algebra, subtract 2 from both sides, and divide by 5, then I wind up with 1/5. And that would be what we call the solution to that algebraic equation. And we can check by plugging this solution in, or back into the algebraic equation, that 2 plus 5 times this proposed x solution, this is 2 plus 1, which indeed is equal to 3. So that is what we know our equations to look like from before this class, or this lecture series. What we would like to do now, we ended last time with a differential equation talking about drag in a body in a body falling through the air. Think like a skydiver. That we wind up with a differential equation that we would like to know how to solve. And what do we mean by solve in this case? We are looking for, so we want a function v equals v of t whose derivative satisfies that equation. And I'll say satisfies star, and I'll label that guy as star. So we need to know two things here. We need to know how, just like in our algebraic equation here, we need to know how to solve for that x and then check that this particular x actually does satisfy an equation. We're going to do the same thing here. We can actually check that a given function is or is not a solution to a differential equation just by plugging it in. So this is actually the easier part. We can check that it's right or wrong just by substituting this function into the differential equation. And the rest of this lecture series is figuring out that other step. How do we figure out which functions give us those solutions? So let's see. If I were to use this example on the notes, so we're going to go ahead and say that this particular function here, let me go ahead and start drawing on this page. Oh, come on, work with me. That's because I have the eraser set. There it is. There's this equation, right? And this equation is our Malthusian growth model that I explained in a couple videos ago. And what I'd like to do is show you that this b of t is actually a solution to this differential equation. And we can step through what has to happen here. So I just need to make sure that if I differentiate this function, right? If I differentiate 7 times e to the minus 3t, then that needs to be equal to 3 times the original function. So 3 times 7 times e to the 3t. And we can check very quickly. The derivative of 7 times e to the 3t, well, I just pull down a factor of 3 from the chain rule. And that winds up giving me a derivative that looks like 21 times e to the 3t. Now, if I were to instead compute what happens if I multiply this function, this b function, by 3, then that is the same thing as this is exactly the 21 times e to the 3t. So this guy, if I multiply the function by a 3, that is the same thing as differentiating the function. So that means that the left and right hand sides of this differential equation are satisfied. So the derivative, oh, get rid of the eraser again. The derivative is equal to 3 times the function. Right? And that's what it would mean to solve this differential equation. So that the function that I substitute in actually creates an equality. Now, that's another question entirely of where that function comes from, and that's not the only function that solves this, as it turns out, and we'll see exactly why very shortly. Now, solutions don't have to look just like a single function or a single expression. I can actually solve an equation across different domains or across different values of my independent variable. In this case, I could try to solve this differential equation, and let's try to get my pen back. There it is. Get my pen back. I'll take a look at this differential equation. This, again, we don't really know where the function is coming from. We don't know why we chose this particular piecewise defined function as a candidate solution, but if we propose that it is a solution, we can check whether or not it is. And what has to happen is I need to satisfy this, I have to satisfy this differential equation on 2 different domains. So for t less than 1 or less than 0, I'm going to use just that function. And when I do, if I differentiate this guy once, that'll get me the y prime. So power rule on t to the minus 1 is what's going to give me that 2 over t squared. And if I differentiate this guy again, I'll pick up the second derivative, which is again a power rule on t to the minus 2. So I pick up a factor of minus 2, and that gives me the y double prime. And on the positive interval, I can play the same game. We'll use a different color here. I can play the same game just with, oh geez, not a pencil. I didn't want a pencil. Why did it pick a pencil? There it goes. We'll use this guy, right? If I differentiate 1 over t squared, again, power rule is going to get me the minus 2 over t cubed. Another power rule gets me the second derivative. And what I'd like to see here is the left-hand side. I want to know what each and every one of these terms looks like. So I need to know what is t squared times y double prime. If I did that for the branch that where t is less than 0, well, it'd be t. I'll do that over here. It'd be t squared times y double prime. So this will be a t squared times minus 4 over t cubed, and that gets me a minus 4 over t. Awesome. And then I ask myself, what does 4 times t times y prime look like? Right, because I'm trying to satisfy that differential equation up there. So I need to know what this second term looks like. Well, it'll be 4t times this guy over here, so 2 over t squared. And this is going to be 8 over t. And then finally, I ask myself, what is 2 times y? So this will be 2 times negative 2 over t, and this is going to be a minus 4 over t. If I add all of these guys together the way the differential equation tells me to on the left-hand side, I notice that t squared y double prime plus 4t times y prime plus 2y is equal to minus 4 over t plus 8 over t minus another 4 over t, and that's going to get me 0. That ensures, that shows me that that this is a function that satisfies the differential equation. And it turns out this 1 over t squared in blue on the notes page will get me exactly another, or it will get me another solution, but it's defined on the other side of t equals 0. Right, so there is this careful interplay of what constitutes a solution and where that solution is defined. And if you'll see up here in the definition, there is a solution space to consider as well. So it's a function. Our solutions to differential equations are functions, and those functions are defined over certain domains that we call solution spaces. All right, so that is where, or what constitutes a solution to a differential equation. So it is important to note that the definition includes the solution space, right? So I very well could just go ahead and define a solution over all real numbers except t equals 0 as to be any one of those two branches, but I can make some jumps if I want to. And this would be exactly where I see what are called regular singularities in my differential equation. But we'll get there eventually. That'll be the chapter 5 material. But this is what constitutes a solution. We are just checking to see that a particular function and its derivatives satisfy some equation. Right? And it's also important to define an appropriate solution. But yeah, okay. Yes. So in the next video, let's see. Yeah. We will go further into